I've been putting off making this video because it's a really interesting phenomena, but I was never sure of the explanation. I think I've worked it out now. I'm not totally sure, but I thought I'll make the video anyway, and then you can decide in the comments what you think about my explanation. So I've got this garden hose, and the head is set to power jet mode. All the water's coming out of just a small hole in the front there. And just to demonstrate how powerful the jet is, I've got this plastic tray. It's made from the bottom of a hummus carton and I can launch that into the air. What's really interesting is if I point the whole thing downwards like this, you'd think with the extra help of gravity it would travel even faster away from the jet, but watch this. It sticks to it. You can sort of move it around. Isn't that weird? So that's what I want to try and explain. Oh my God. To try and explain it, I want to show you what I think is the same effect, but with air instead of water. And for this, you need a hairdryer and some polystyrene and a second sheet of polystyrene like this. If you're going to do this, make sure you've got a hairdryer where you can turn the heating element down to 0. So you blow the air out. I can feel the jet of air pushing my hand down. But if I lift it up to a certain point, it gets sucked up. So there you go, the polystyrene is defying gravity, as some people like to say. Of course it's not, it's just there's some force counteracting gravity pushing up. Let's see if we can figure out what that force is. Think about the air flowing out of the hairdryer. It's being forced to travel through the cavity between the two layers of polystyrene because of the air pressure produced by the hairdryer, which I'm going to assume is fixed. So I've created this animation of the particles in the air. This animation is missing certain details, like it doesn't show any thermal energy. Because the temperature of the air is somewhere above absolute 0, it has some thermal energy. So really, these particles in the air should be bouncing around in all different directions, hitting each other and that sort of thing. So what you're really seeing is the average smoothed out motion of the particles, ignoring thermal motion. I've created the animation in such a way that the density of particles is the same everywhere. So if you look at the density out here towards the edge, it's the same as the density towards the middle. That's because I'm assuming that the pressure is the same everywhere. And if you want the pressure to be the same everywhere, you need the density of particles to be the same everywhere. And you know this intuitively from playing with an air-filled syringe. If you compress the syringe, you increase the density of the particles inside, but you also increase the pressure. You feel that increased pressure as the syringe pushing back against your hand. But is it right to assume that the pressure is the same everywhere? Probably not. And actually, we've neglected to think about the velocity of the gas particles, because velocity doesn't change. Like, an object's velocity will stay the same unless that object is acted on by a force. Like, if an object is drifting through space, it will continue to drift at a fixed velocity unless a force acts upon it. And that's true of the particles in this gas as well. And we're interested in the sort of net velocity, the outward drift velocity of the particles, as opposed to the thermal velocity of the particles. So in my animation, to keep the density of the particles the same, I've had to slow them down as they travel outwards. But let's for a minute assume that the particles aren't being acted on by a force, so they wouldn't slow down. Their velocity would stay the same. What would it look like? So here's a different version of the animation where the velocity of the particles don't change. And you can see how the density changes as you move out from the center. There's just more space around the edges than in the middle, so there are fewer particles to go around per unit volume. The reality is probably somewhere between the two animations. But the point is, the density of particles is going to go down somewhat as the air streams outwards. And it seems like, at least for the case of the hairdryer and the polystyrene, that the drop in pressure is enough so that the difference in pressure between the air inside the cavity and the air underneath the cavity is great enough to overcome the weight of the polystyrene pulling it down. So just so you've got the whole picture then, you've got normal atmospheric pressure underneath the polystyrene pushing it up. You've got the pressure inside the cavity pushing it down, but that's less than atmospheric pressure. And then you've got the weight of the polystyrene pulling it down. And they're all in balance, so the polystyrene doesn't fall. My theory is it's the same principle at play with the water jet and the hummus tub, which explains why you can't get it to work with just the end of a hose. You need to have a small jet embedded within a flat plate like we've got here. And we have the same thing with that power jet hose connector that I was using. A lot of people are probably now shouting at the screen, Bernoulli, it's just Bernoulli, say Bernoulli. And I get that, I like shouting Bernoulli as well. But I didn't use Bernoulli to explain what was going on here. And the reason is, like, Bernoulli's principle is a derived principle. What I mean by that is you can look at the underlying principles of fluid dynamics and you can derive this thing, and you can say, look, by rearranging all these equations and stuff, I can show that this thing is always true. This simple relationship between pressure and velocity is always true. And that's really useful if you're doing fluid dynamics. But I don't think it's useful for giving someone a truly intuitive understanding of what's going on. One last thing I want to show you that's somewhat related, but probably has a slightly different explanation. Take a hand blender like this one and a container that is slightly larger than the hand blender. Put some water in there and turn it on. The effect is actually really strong. Using these travel scales, it looks as if the pulling force is equivalent to the weight of almost a kilogram under gravity. But is it the same effect as the downwards jet of water? Maybe not, actually. The blades of the hand blender act like propellers. They draw liquid upwards. So it's different in that way. I don't know. I feel like it's got something to do with surface tension as well. At least surface tension would certainly play a part. Probably does in the downwards water jet phenomena as well. Anyway, let me know what you think in the comments. I built those animations in JavaScript and HTML5 canvas, which is something I didn't know how to do until I learned. These days, I really see the benefit of taking online video classes, and I'm really happy that the sponsor of this video is the best provider of video classes that I've been able to find, which is Skillshare, an online community of learners that has thousands of classes covering creative and entrepreneurial skills. You know, in the old days, if I'd had a challenge like this, I would have tried to hack something together with code that I found online, and eventually I'd get it to work, but I wouldn't understand why or how. But this time I started by taking the Get Creative with HTML5 Canvas course on Skillshare. And yeah, of course I still knit code online because that's how you code, but the process of getting that code to do what I wanted it to do was much quicker because I truly understood how the coding works. And that's what I see as the benefit of online video classes. It's like an acceleration that gets you to where you want to go quicker. And it's a speed boost that stays with you. Like the next time I need to solve a problem like this, it will be quick again because I still understand. You might also like their basics of web design layout class, or if animation is your thing, they have classes in other technologies like After Effects. It's really affordable, $10 a month for an annual membership, but because they're sponsoring this video, you can get a 2-month free trial if you go to school.sh/SteveMold3. That's school.sh/SteveMold3. The link is also in the description. Check it out today. I hope you enjoyed this video. If you did, don't forget to hit subscribe, and I'll see you next time.